Let me do a sound check real quick. Can everyone hear me all right? Great. Okay, we'll go ahead and start in a couple of minutes. All right. We'll go ahead and begin in 1 minute. I think so far at the moment, Chris, it is only you. However, I know some people have been watching the videos afterwards. All right, I guess we'll go ahead and begin. First of all, has there been any questions or any difficulties with the material so far? All right. So for today, we are going to be covering the material up to and including the Boston housing prices project. That will include talking about model evaluation and validation. Going through the material really quickly because I want to spend most of the time focusing on the project itself. First of all, accuracy is how many times the model prediction is correct. Generally, with regards to machine learning, we want to use metrics that are more complex to better analyze the problems that we are addressing. Two terms that you should be familiar with are type 1 and type 2 error. Type 1 error are false positives. That's where if you predict that it's positive, but it's actually negative, that would be a type 1 error. And type 2 error would be considered a false negative. That meaning that you predict it to be negative when it's actually positive. Now, we can use these terms of false positive and false negative to create terms called precision and recall. You can think of precision as the accuracy of the positive predictions. It's the percentage of positive results that you accurately predicted over all the positive values. So that would be true positive over true positive plus false positive. That's the precision. You can think of it as in the diagram here, the left two. And you can think of recall as the number of true values that you manage to that your model managed to accurately predict. So it'd be the true positive over true positive plus false negatives. With regards to the best times to use them, so one example would be that you want to find all the sick people. You're okay with accidentally bringing predicting some people to be sick when they're not, but you must find all the sick people. In that case, I'm going to go ahead and ask the chat here. What do you think you would use? Would you use precision or recall if you're trying to identify all the sick people and you're okay with accidentally predicting some healthy people to be sick? Right. So looking at it, we want to diagnose all the healthy or all the people that are actually sick, but we're okay with getting some false positives with the healthy people. So yes, it will be recall that you use. Now compare that to another example. Let's say that we want to punish false positives, spam mail more than false negatives for email, right? In that case, yeah. So these are just two examples that you can look at here for using either recall or precision for different examples. From problem to problem, you really have to figure out for yourself whether it's more important to have fewer false positives or fewer false negatives. One way in which we can take advantage of both precision and recall are with the F beta score. Another name for it is the harmonic mean of precision and recall. And the F beta score is essentially a balance between the precision and recall, where it's precision times recall divided by precision plus recall, multiplied by a constant that you determine beforehand to determine whether or not you want the score to lean more towards precision or more towards recall. And another way of saying that would be, do you want more false positives or more false negatives in your model? And accounting for that with a final score that you can use for your metric. I have some code here for how to implement it using, see, is this it? Yeah, so this is just showing precision recall and F1 score. F1 is where you have a perfect balance. So it's called F beta because you can change the value of beta to lean more towards precision or recall. If you set beta equal to 1, then the metric will evenly look at precision and recall. All right. Are there any questions so far? Okay. So then with that, let's go ahead and jump into the project for predicting housing prices. For this project, what we'll be doing is we'll be familiarizing ourselves with the NumPy, Pandas, and scikit-learn library and applying them to a regression problem where, given some data for houses, we want to accurately predict the prices for the houses. So in this project, you will evaluate the performance and predictive power of a model that has been trained and tested on data collected from homes in the suburbs of Boston, Massachusetts. A model trained on this data is seen as a good fit, could then be used to make certain predictions about a home, in particular, its monetary value. The data set for this project originates from the UCI machine learning repository. It's a very famous data set. It's used in a lot of introductory courses. It looks at about 14 features for homes from various suburbs. And for this project, the following preprocesses have been made to the data set. So 16 values have a value of 50. So these data points likely contain missing or censored values and have been removed. One data point has an RM value of 8.78, which this data point has been considered an outlier and has been removed. they have 4 features which are deemed essential, and the non-relevant features have been excluded. And finally, we have scaled the prices to account for 35 years of market inflation. So if we go ahead and run this first cell here, we get that the Boston housing data set has 489 data points with 4 variables each. So that's what we're going to be looking at overall. We have set our prices value equal to data of MEDV, and we have put everything else into a variable called features. So the first step that we are going to do here is that we're going to explore our data. And for the first part, what they want you to do is they want you to determine the minimum price, maximum price, mean price, median price, and the standard deviation, and then output that. And they want you to use NumPy for all of this. So I'll go ahead and walk through the first ones with you. So what you can do here is if you just type in Google NumPy minimum, you'll come across several definitions of minimum. We don't want to use this minimum, which compares the minimum between 2 arrays. We want to use amin, which returns the minimum of an array or a minimum along an axis. So going back to our notebook, we are going to type in, because we imported NumPy using NP, or NumPy as NP, we're going to np.amin. And because we already saved our prices under the variable prices, we can just type prices here. And you'll see that it'll return a minimum price if we run that cell. Likewise, to determine maximum price, there are several ways you can do it. But NumPy also has a variable called amax. So we'll go ahead and use that here. And we get a maximum price of $1,024,800. All right, so I'll give you guys now an opportunity to look up the mean price. And could you please put in the chat what the method is from NumPy in order to output the mean? All right, so if we Google NumPy mean, we get that it's just mean. All right, so basically you just do that for each of these, and that should give you the values for the maximum, minimum, median, mean, and standard deviation. Are there any questions so far? Okay, I'm going to move on then. So as a reminder, we're going to be using 3 features from the Boston housing data set. Just going over them really quickly, RM is the average number of rooms amongst homes in the neighborhood. LSTAT is the percentage of homeowners in the neighborhood considered lower class or working poor. PT ratio is the ratio of students to teachers in primary and secondary schools in the neighborhood. And they want you to use your intuition for each of the few features above and determine whether you think an increase in the value of that feature would lead to an increase in the value of the housing price, or a decrease in the housing price, and justify your answer for each. All right. So just walking through the logic here, I'll just go for the first one and I'll let you guys work through the other two. But with the rooms, usually a house with more rooms will be more expensive. So with I would expect then as the number of rooms increases, then the price of the house will increase. All right. Likewise, going through LSTAT and PT ratio, if there's more lower class or working poor, then you would assume that the people have less money, and therefore the housing in that area would be cheaper. If the percentage of homeowners that are poor is increased, so this would be inversely proportional to the housing prices. And the PT ratio is the ratio of students to teachers. So if there are more students for each teacher, you would assume that neighborhood is also poorer. So it would work exactly the same way as LSTAT. So in this case, RM would be directly proportional and the other two features would be inversely proportional. So now that we've developed an intuition on how to use the features, we now move on to developing a model. So there are several metrics that you could use, such as the F-beta score that we talked about earlier. However, for this project, we are going to be using the coefficient of determination, or R squared, to quantify the model's performance. You can go ahead and click on this value here to read what R squared is. But in a nutshell, if the value of R squared is closer to 0, that means that the dependent variable cannot be predicted from the independent variable. So if it's closer to 0, that means there's little to no correlation, versus if R squared is closer to 1, that means that there is a high correlation between the output and the input. And again, if you want to read more about that, feel free to click on the link here. So what we want is we want a model with the highest score possible. And they want you to use the R2 score from sklearn metrics to perform the performance calculation between Y2 and YPredict. To import that library, we can do from sklearn.metrics, import R2 score. And in order to figure out how R2 score works, what we can do is we can look it up. So I can type sklearn R2 score. And it says right here that we pass in the true values followed by the predictions, and that should give us the result. And they also usually have an example at the very bottom of how to use it. So how to import the library, and then how to use R2 score. So going back to here, we want to then use R2 score. And we're going to be using Y2, Y-true and Y-predict to calculate the R squared, and then we'll be returning that value. So now anytime we run the performance metric method and we pass in the true values and our predicted values, then this will calculate and return the performance score between the true and predicted value based off of the R squared. If you want to use a different metric, all you'd have to do is change this metric right here. Instead of R squared, you could use F beta, you can use something else, and therefore you can change your metric. So for this question, what they want you to do is, given this data set here, we have these true values and these predictions. They want you to run the performance metric function and calculate the coefficient of determination. That's as simple as running this cell down here once you've completed the performance metric code. And I'd like to validate with with the people who are watching to make sure I have the same thing as you. But when I run this, I get an R squared value of 0.923. So now they ask you, would you consider this model to have successfully captured the variation of the target variable? Why or why not? So remember, if the value is closer to 0, that means that we're not seeing a dependence between the true value and the predicted value. Just eyeballing this data right here, though, you can see that the true values are usually fairly close to the predicted values. So you would expect to see an R squared value closer to 1, which is exactly what we see right here. Therefore, I would say that the true value and the predicted value are highly correlated. All right. Are there any questions so far? And if we were to see a low value for our R squared, what that would mean is that our model is not making good predictions. So therefore, we'd have to change our model in order to increase the validation score. For the next portion, we'll be looking into shuffling and splitting the data. And this is to help with our validation of the model itself. So the first thing that they want you to do is they want you to import the train test split from sklearn cross-validation. So the way we'll do that here is from sklearn.cross-validation. As it's shown here, we will import train test split. And then we'll be using train test split to generate our training set from our features, as well as our test set from our features. And then we'll be generating the labels for the training set, as well as the labels for the test set. Looking into how train test split is used, we see here that it takes in a sequence of indexable arrays. And we have to pass in our training set, our labels, our test size, and our random state. And it says within the instructions to set the random state and to a value of our choice. Looking up above again, our features, our X set is called features, our Y is the labels, which is prices. So we're using our features, our prices, test size. Test size by default is 25%. They want 20% for testing. We'll set test size to 20. I believe that's correct. Oh, 0.20. And we'll set our random state equal to 1. Let's go ahead and run this. All right, and then the next question they ask is, what is the benefit to splitting a data set into some ratio of training and testing subsets for our learning algorithm? So chat, why do you think it's a good idea to split our data into a training set and test set? I'd like to hear some of your thoughts. Why do we need a testing set in addition to the training set? I'll give you guys a few moments to think on that one. Right. When you have, so normally what you'd have is that you'd have the training set, which you use to build your model, and then you just deploy it into production and hope that your trained model performs well against the production. When you split your data into a training set and a testing set, what you can do is you can use your testing set as a pseudo production training set. So what I mean by that is you can run your model against the training set, and what may happen is your model may overfit or underfit your training data. If it underfits, that's fairly easy to catch. That means that the training set will have a low accuracy when run through the model. But if it has a high accuracy, you don't know if your model is good or if it's overfitting. So we can use our test set to validate our model and verify how well it runs and verify that it's not overfitting the data. Does that make sense to everybody? And thank you, Chris, for the answer. Okay, moving on to analyzing the model performance. For this third section, we'll be looking at several models learning and testing performances on various subsets of training data. Additionally, you'll investigate one particular algorithm with an increasing max depth parameter on the full training set to observe how model complexity affects performance. We'll be graphing the model's performance based on varying criteria that can be beneficial in the analysis process, such as visualizing behavior that may not have been apparent from the results alone. So the following code cell produces 4 graphs for a decision tree model with different maximum depths. Each graph visualizes the learning curve for the model for both training and testing as the size of the training set is increased. And if you want to look at the code again, this is under the visuals.py. So if we take a look here, we see that we have decision trees with a max depth of 1, which means we are asking 1 question, a max depth of 3, which is where we're asking 3 questions, 6, and 10. On the side, we have the score, or how well it is performing. Our training score is on top in red, and our testing score is underneath in green. And the x-axis here is how many training points we use to train the data. You'll see here between the 4 models that the gap between the training score and the validation score varies, as well as the overall score of the models themselves. You'll see here that as we increase the max depth of the decision tree, our training score will perform better and better. We'll get an R-squared score closer and closer to 1 as we continue training with more and more data. You'll notice with our testing score that as we have more max depth, after a certain point, you won't be seeing much improvement in performance. As a matter of fact, as you get past a certain point, you'll actually see a decrease in performance from the maximum depth. So what you're looking for here is you're looking for the point in the model where your validation set is performing as ideally as possible. The best way to eyeball it is just taking a look at the gap you see right here between the two sets, between the training set and the validation set, you'll notice that when we have a max depth of 1 and a max depth of 3, the gap between these two models is very small, which means that both the training set and the test set are performing equally well as we have more training points. As we increase our max depth for the decision tree, that gap will widen as our model begins to overfit. So generally, once you start seeing this gap here widen, that means that your model has hit around peak efficiency and is starting to lose efficiency. So you'll want to choose a model around there. So the next question, question 4, they want you to choose one of the graphs above and state the maximum depth for the model. So that being either 1, 3, 6, or 10. Then they ask what happens to the score of the training curve as more training points are added. So as we move along the x-axis to the right here, what happens to the model itself? What happens to the testing curve? So as an example here, I'm going to go ahead and choose max depth equals 3 just to talk about that one. You'll notice here that as we add more training points to our model, at first there's a dip in performance as it drops from 1.0 down to 0.8. And as we keep going, as we add more training points, our training score stabilizes here. And it stabilizes a little bit above 0.8. Compare that with our testing score, where as we have more training points, our testing score improves overall. It starts off pretty low at when you have 50 training points at around 0.6, but as you go up to about 350, it starts getting closer and closer to that 0.8 threshold. Then they ask, would having more training points benefit the model? What you're looking for here when they ask that is you're looking for how the slope of the model changes with more training points. I would say that with a max depth of 3, beyond 350 training points, you will not see much improvement. It feels like it looks like the model here has about stabilized around 0.8. You're not going to see any more improvement, or if there is improvement, it will be infinitesimally small. This is actually very good to use because a lot of time when you're training your models, you'll have to ask yourself, how much data should I use? Because the more training data you have, the longer it takes to train your model. When you're training in the real world, what you want to do is that you want to get your model to peak efficiency as quickly as possible. So we want to use the smallest data set possible to train our model as quickly as possible to push it to production and have it perform optimally as soon as possible. So looking at graphs like this are great for helping you visualize how many training points you should be looking to use. Just taking a look here, you can see that if you had only 50 training points, your model would not be ideal. So you'll generally want more than that. With a max depth of 3, I'd argue that you reach peak efficiency around 300. So you wouldn't need any more data than that. 350 would just be overkill. So going down to this question here, they ask you if your training and testing curves are converging with a score above your benchmark threshold, would gaining more data be necessary? Think about the pros and cons of adding more training points based on if the training and testing scores are converging. So hopefully I've helped point you guys in the right direction with that question. The next question, however, deals with complexity curves. So I'm going to go ahead and run the cell now. The following code cell produces a graph for a decision tree model that has been trained and validated on the training data using different maximum depths. The graph produces two complexity curves, one for training, which is in red, and one for validation, which is the bottom one in green. Similar to the learning curves, the shaded regions of both the complexity curves denote the uncertainty in those models. And the model is scored on both the training and validation set using the performance metric function that we wrote above. So we see here that as we increase our maximum depth, there's a gradual increase in performance for the training score, but after a certain point, the validation score actually starts to lose accurate, or it starts to decrease in performance. For question 5, they ask, when the model is trained with a maximum depth of 1, does the model suffer from high bias or high variance? And just so that you guys know how to eyeball it, high bias is where both the training set and the data and the validation set have high error, whereas high variance is where the training set has low error, but the validation set has high error. So taking a look at when there is a maximum depth of 1, in the chat, do you guys think that there is high bias or high variance? At the beginning here, is there high error in both the validation score and the training score, or is just the validation score underperforming? High bias, that's correct. Then they ask, what about at a maximum depth of 10? Because at a maximum depth of 10, the training score is performing very well, but the validation score has decreased in performance. Therefore, you're suffering from high variance. And high bias is a sign of underfitting, and high variance is a sign of overfitting. So taking a look at this model, we see that the validation score tends to perform the best here in the middle. It starts to drop off at around 6. So I would argue the best performance is around 4 or 5 layers, or 4 or 5 depth. Let's see here. So question 6 is just asking that. But at which maximum depth do you think results in a model that best generalizes to unseen data? And what intuition led you to this answer? Are there any questions on the material so far? Okay. Feel free to ask any questions you have in the chat. Otherwise, I'll be moving on to the final section, which is evaluating model performance, where we will be constructing a model and making a prediction on the client's features set using an optimized model from FitModel. Going back to the lessons, one of the sections covered was grid search. Can anybody in the chat describe what the grid search technique is? And if you need a reminder, I believe grid search is covered in the classroom. Let's see, I think it's under model selection. No. Yeah, section 8. Lesson 8, section 10, or section 8, actually. All right. And yes, the grid search technique is to find optimal hyperparameters amongst different sets of them. So when we're applying it to a learning algorithm such as this, they ask, how can it be applied to optimize the algorithm? So in this case, what parameter? I would say that in this case, you could probably use the maximum depth of the decision tree to optimize your algorithm, as you're trying to find out at which point of the maximum do we have a decision tree with the optimal maximum depth to optimize performance. Yep, that's correct, the depth. All right. Question 8 is with regards to k-fold cross-validation. Because we're running out of time here, I'm going to go ahead and let you guys answer that question regarding it. But moving on to the final section here, fitting a model. We'll be using a decision tree algorithm for it. You'll train the model using the grid search technique to optimize the max depth parameters for the decision tree. And we will find our implementation using the shuffle split for an alternative form of cross-validation. It's not the same as the k-fold cross-validation technique, but it's just as useful. It will create 10 n-splits shuffled sets, and for each set, we want to use 20% of the data for the validation set. So in order to run this, we'll have to import several things here. We'll have to import from sklearn.tree, import the decision tree regressor. We'll have to import from sklearn.metrics make scorer. And finally, from sklearn.grid search, we'll have to import grid search CV. If you open up each of these guys, you can just right click and open a new tab. It will show you what parameters to pass in and how to use it. So for the first step, we need to create a decision tree regressor object. Decision tree regressor, I believe. If you want, you can set the random state for it. State. By default, it doesn't have a random state. So this is if you want to seed your model. I don't believe for this project they ask you to seed it. No, they don't. Great. Next, they want you to create a dictionary for the parameter max depth with a range from 1 to 10. So I believe what you can do for that is you can do is equal to x for x in range 1 to, I believe if you do 11, that's it. Let me verify this real quick. Yes. Now you have to do 11 instead of 10, because if you do 10, it'll only go 1 through 9. Need to provide the parameter name. Oh, that's right. Yes. Thank you. Depth. That. Okay. And then we need to transform the performance metric into a scoring function using make scorer. To use make scorer, we can right click that, open it up. So we just we provide a function, and that becomes our performance function. Is this the right one? Make scorer. Yeah. Okay. Make scorer. Now we're passing in the performance. Well, didn't mean to do that. We will be passing in the performance metric. And then finally, we will be creating the grid search CV object. CV. Again, we'll take a look at how it's being created. We have to pass in the estimator and the parameter grid. So you either need to provide the score function or scoring must be passed. And then we need to assign it to the grid variable. Professor params scoring FNC CV sets, I believe. I'm reading this correctly here. Just verify. Estimator. All right, so now we can go ahead and run the next cell down here to verify it. Model. Shuffle split has no items. Okay. Scoring. Did I do that right? I did not. Okay, the estimator is regressor. Parameter grid is params. Scoring function Okay. Hold on 1 second here. I did something wrong. So let me verify I declare my parameters correctly. Yes. Okay. Next score. Let me verify I use that correctly here. Score function. Okay, but while I'm figuring this out, are there any other questions regarding the material? We're just about running out of time here. I don't think that has anything wrong. It's CV sets. Interesting. Let me go ahead and walk through this real quick. Regression, grid.fit xy. Yeah, so the grid is failing because shuffle split has no attribute items. So something wrong with the shuffle split. Oh, okay. Let's try that. There we go. Yeah, thank you for that, Chris. All right. So you need to put scoring equals and CV equals for it. Yeah. Exactly like here. Scoring CV. And then you can just put this for your final answer here. All right, moving on to question 10, which is predicting selling prices. So imagine that you're a real estate agent in the Boston area looking to use this model to help price homes owned by your clients that they wish to sell. You have collected the following information from 3 of your clients. Client 1 has 5 rooms, client 2 has 4 rooms, client 3 has 8 rooms. Neighborhoods are 17%, 32%, and 3% poverty level, respectively. And student teacher ratio of nearby schools is 15:1, 22:1, and 12:1, respectively. And they want you to now recommend a price to each client for them to sell their home at. And they then ask if the prices seem reasonable given the values for the respective features. In order to do this, they have already provided you the client data within a matrix. All you have to do is run the cell here. So for the first home, for 5 rooms, 17% poverty and 15:1 student to teacher ratio, they recommend 424,000. For fewer rooms, a higher poverty neighborhood, and more students per teacher, they recommend a price of 284,000. And for a house with more rooms, 3% poverty level, and 12 students per teacher, they recommend a value of 933,000. So, does that seem reasonable to you? And just to save time here, I would argue that yes, as the Client 3 has the room with the house with the most rooms, lowest poverty level, and fewest students to teachers. So their house would make sense to be the most expensive. Client 2 has the fewest rooms. Their house is in the neighborhood with the highest poverty rate, and it has the most students to teacher. Therefore, it would have the lowest price. And client 1 has the in between, so 400,000. Taking a look at the sensitivity, an optimal model is not necessarily a robust model. Sometimes a model is either too complex or too simple to sufficiently generalize to new data. Sometimes a model could use a learning algorithm that is not appropriate for the structure of the data given. Other times, the data itself could be too noisy or contain too few samples to allow a model to adequately capture the target variable. So in this case, what we did is that we just ran our predict trials 10 times with different training and testing sets to see how the predictions for a specific client changes with respect to the data it's trained on. So running it multiple times, you'll see right here that there's a range of $73,000 in the change in price. So what this is showing you is that if you run the model multiple times, depending on how you seed it, you may get different results each time. And that's something to keep in mind whenever you're generating a model. And the final question they ask is, discuss whether the model should or should not be used in a real world setting. So taking a look at the range in prices here, they want you to use comments. They want you to take a look at this data and then answer if this model would be applicable in the real world. So the first question, some things they want you to think about. How relevant today is data that was collected from 1978? How important is inflation? Are the features present in the data sufficient to describe a home? Do you think factors such as like quality of appliances in the home, square feet of the plot area, presence of pool, or etc. should factor in? Basically, they're asking if you only knew the number of rooms, the poverty level, and the number of students, teachers in nearby schools, would that be enough information for you to buy it, to predict the price for a house? Would data collected in an urban city like Boston be applicable in a rural city? And is it fair to judge the price of an individual home based off of the characteristics of the entire neighborhood? So what they're leaning towards here is saying that given the data itself, you shouldn't apply this model to a real world, not unless you change the data itself such that it took more information in. You want the data to be more up to date. You want the data to have enough features. Exactly. It's too simplistic. Yeah, you would need a more complex model in order to be able to apply it. And even then, the model you generate will only be applicable to the data that's passed in. So you need to watch out for that whenever you train a new model. Okay. Are there any questions regarding the project overall? I hope that this session helped walk everyone through what is needed to be done for this project. While I'm waiting for people to type questions, after this section, the material will next be going further into the different algorithms that you can use to create your model, going from linear regression, perceptrons, decision trees, which is what we just used, naive Bayes, support vectors, and at the very end, which is what we'll be covering next week, we'll be covering the supervised learning project. So that will be your homework for this week, is to get as far along as you can to work towards the Finding Donors project, which is lesson 18. If you have not already, feel free to schedule a one-on-one with me and I will help you out as much as I can. Otherwise, my office hours will be every Wednesday going forward from 7 p.m. to 8 p.m. I will also be trying to hold each of these online webinars every Thursday from 7 p.m. to 8 p.m. Otherwise, feel free to reach out to me on Slack. And after this, I will post up a Calendly link so that you may sign up for one-on-ones with me. Thank you very much for attending, and I hope you all have a good week. Oh, and also I will be posting this video up on the Slack channel afterwards.